this is kind of some general slides I have, just an overview of OpenRAM. So I wanted to kind of get some, feedback from people and so on. It's more of a kind of an overview of how I envision the project, what it's for, and kind of how it's moving forward and so on. As you mentioned, there's tons of challenges with memory generation. And I think the more I get involved with it every year, I keep seeing the number of challenges are actually even more than I thought. And so it's kind of good that I jumped into it naive, and then now I'm kind of figuring out everything and how it has to work. So and the reason I started the project was basically no one else wanted to do it, right? No one else was making an open source memory compiler.
That's true.
In grad school, it was always a challenge to get even standard cells, and design kits. We're now seeing kind of high level languages that you can get and IP in terms of processors and stuff, but really memories are kind of that one component, along with like some things like PLLs and really process specific things that are hard to get without really licensing from a particular vendor. And so that's why I kind of wanted to address this problem. And so, this is more for a general audience. I think most people here know, what a memory compiler is. Memory is it's a component for your design flow. You can treat it as a black box from a design perspective and use it in your place and route flow. In terms of actually designing memories, it's not quite pure analog design, but it has a lot of analog aspects to it. And so therefore I kind of show the trade-offs from the RISC-V analog design book where, they talk about more for amplifiers and things like that, noise and gain and things like that. You have a lot of these same trade-offs in kind of this trade-off octagon with memories, except your main thing is probably area or memory density, and in addition to power and all the other issues. So, it's not just a, digital, does it work or not, but you have to worry about many other complexities in the design of memories. And so for that reason, there aren't really tool flows to design memories very easily. There's a lot of customization and things like that. And so now I also want to emphasize that I'm really focusing on kind of just single array generation. I'm not really focusing on caches right now or very specific memories like, highly ported register files. Those are all on the roadmap. I'm actually working with a student in Turkey to make a cache generator using OpenRAM, but that's kind of a higher level optimization. And so, but OpenRAM, there's a couple other goals that I want with OpenRAM just at the bank level. And, I had this frustration where I started looking at this, and memory compiler is not a new thing. Every company has their own, if they do high performance designs, Intel, AMD, and so on. They may not actually be compilers per se, in that they may generate a couple memories that they then use, and those are highly optimized usually. There are other companies that sell compiler kind of infrastructure. ARM is well known as selling IP. All the other big three, I think, have Cadence, Synopsys, probably and Mentor Graphics as well, actually. One of my students from OpenRAM went to work for Mentor in their memory unit. And so they all have, things to help with memory design. But there was nothing open source. And so that's one thing. These all require expensive licenses and so on. Now, there were some academic things. Most of these were not complete memory compilers. They did what they were good at. I don't even cite here Cacti, which is a famous architectural simulator of, what is the power performance of a cache. That's well known in architects. But then at the array level, there's things like FabMem, which generates just a black box based off of Cacti models. FakeRAM, which is similar, I think. Actually, FabMem, was actually a technology using Cadence tools in one technology. FakeRAM was a black box. And then there were a couple scripts like PotStill, which just does array generation. And then actually AMC, Asynchronous Memory Compiler, which is actually a fork of OpenRAM. And we're working on getting the features of AMC in OpenRAM actually with the Yale people. So that's, but the main thing with those is they were kind of limited in that they weren't complete. Like they didn't have control logic in the case of pot still, or they were for one technology, or they relied on commercial tools and to do the design, like with skill and cadence. And so we wanted to address that. Now, I always like to think of this in terms of being an optimist and a pessimist. In terms of the glass half full, why do you want to have an open source memory compiler? Well, you want it to be, many of them are free but don't have limited information. So you have limited information. So you want to make that available so you can see into the memory stack. Memories are the bottleneck for performance and area and power typically. So they're an important part of design. Technically, memories have a very regular structure. It's a lot of people, you ask a software designer, why is a memory compiler hard? It's just a nested for loop, right? You make the rows and columns and you're done. Well, it is true, but then there's the control logic and all the peripheral circuitry, which is actually very complex. And then, open cell libraries and PDKs are available, but not memory IP. So those are kind of these are like the benefits of like why we actually want to have memory compilers. And then you get to the process and circuit people. And I already alluded to a couple of those, and they're like, well, you can't have an open source memory compiler. It's just not possible. Bit cells are proprietary. The lithography alone, you can't see it. They won't tell you what it is. The cells are black box. We're seeing changes now, with like the Skywater technology, where we actually have the actual bit cells with lithography enhancement from Skywater. We support basically foundry bit cells where you could treat them as like a black box, or you could also make user design rules memory cells and so on. But then the second issue is, to make memories and make sure that they work, you actually have to tape them out. Unless you have silicon proven IP memory, people don't really, they don't believe that your memories are good designs. And that's realistic, right? You have to make sure they work. And so we're working on that now with a number of technologies. Also, design rules are typically not accessible, so it's hard to access that information and then to distribute that information. We try to work around that with OpenRAM by using a number of open PDKs as examples and reference designs. And we feel like if we are compatible with a large number of these open PDKs, we're going to basically accommodate all of the quirks of most of the newer technologies, because we're kind of being flexible with what information we use. And then, a lot of designers really don't care about the memory compiler itself. They just want some IP for their situation. They want a memory of this size with this data width. And, the thing we're trying to do with OpenRAM is keep it flexible so that we can have more customization. Memory designers often, or I should say system designers often had to compromise in their design with what memories were available from existing solutions. And so we want to basically offer more options to basically have them have a more customized solution for their designs. And that comes with benefits, but also disadvantages too. So the principles of OpenRAM are basically, we want OpenRAM to be this kind of glue framework that holds together things around memory. And we want it to be usable by hardware engineers so that they can make designs. We want it to be extensible by both hardware and software engineers as well. So we want the hardware engineers to customize which types of memories they want. We want software engineers to be able to use this in larger infrastructures, such as machine learning chips, where you may want a unique memory architecture. So we want software people involved as well. We also want it to be maintainable. And I think we take a lot of principles from software engineering in that aspect, where we have a lot of unit tests to make sure things don't break through different technologies. And we're also starting to track basically quality of results of memories as we improve the design as well. Number 4, we want it to be portable to any technology. And this is where it gets difficult because, as we know, every process technology is a little unique in different ways. And the way we kind of accommodate that is by basically paying attention to the unique process stuff where it really matters, and where it doesn't matter, we try to make conservative assumptions to be more compatible with other technologies. So kind of the idea of restrictive design rules, where you may say, oh, this, just do the easiest thing rather than the thing that gets you the most density if area doesn't matter in something. Like the example I like to point out is in the control logic, you use a couple NAND gates. We don't need the area of those NAND gates to be highly optimized because you use like 3 of them. And so that doesn't really affect your overall area of your memory. But if it's in the decoder logic, for example, then it's replicated in the entire side of a memory and it does matter. So we try to focus on things that really have an effect. And then the last thing is being independent of any particular tools or methodologies. We want to be able to work with commercial tools and with open source tools. We know that companies do rely on commercial tools for their designs, and so we want them to be able to use OpenRAM. But we also want to support the open source flows, and so that anyone can download stuff and use it right away. And I think this gives us flexibility for both parties in that regard. In terms of open features of OpenRAM, I added Chips Alliance to this slide now, since we officially are an associate member now. UC Santa Cruz is rather, but the OpenRAM project too. We're working with a number of these open source consortiums and so on. We provide 3 reference designs, free PDK, scalable CMOS, and I'm still working with Tim at Google to open up the Skywater repo, but it's basically there, and we're generating single port and dual port memories. And so we just taped out a bunch of it. We are taping out a bunch of example designs right now for that. And then we provide basically a number of things that wrap around memory design. So we also provide basically a characterization methodology of memories and functional verification. So this uses backend SPICE tools. I've actually upgraded this to use SICE, the highly parallel SPICE simulator recently with the support of Eric Kiter. And that's something that's actually kind of pretty exciting. It's very fast. And then we also do a lot of the general file formats, so GS, SPICE, Verilog, reports, and so on. And then we basically provide kind of wrapper scripts for basically the different verifications, so LVS, DRC, and simulation around commercial and open source tools, so that we don't depend on the certain features of a tool to do the verification. Because we know, for example, every SPICE simulator is somewhat unique in the way it does simulations. It has a custom command or whatnot. And so we try to basically abstract those away so that we can support all of the different tools. The one I'm actually adding very shortly is K-layout. I have actually a number of pull requests for K-layout for DRC and LVS. And so that should be in there in the next, probably within the next month as well. I mentioned if there's questions, interrupt. Yeah.
Yeah, sorry, Matt. So are there any challenges in terms of interfacing with commercial tools or ensuring that nothing proprietary of the commercial tools end up in the data that is generated? I know certainly both Cadence and Mentor, or now Siemens, have some peculiarities around some of these things. Like I know, like with respect to DRC, that Mentor is particularly protective of that language, as I painfully learned in my earlier life.
Yeah, so we don't actually include any of that stuff in OpenRAM. So we rely on basically pointers to your PDK that have those rules. So we keep that all separate. The only thing that we may use is the public APIs of a simulator or tool, or command line options. And that brings a good point. There's a number of simulators that I don't use. Like I have a user contributed, I forget what the simulator is, XA from Synopsys. It's another circuit simulator.
Yes, right.
I have support for that, but I don't run that because someone added the support,
Okay.
And so there are a number of them, and I guess maintaining those is an issue when I'm not actively maintaining all of them. So, but we're relying on user feedback for that.
Sure. That makes sense.
Yeah.
Okay.
And of course, we don't do any benchmarking with commercial tools because we're not allowed to do that with our licenses. So
I understand that too.
Yeah. Yeah, and that goes back to, I want to play well with commercial tools too. I'm not trying to get rid of them. I'm trying to augment their flows to use an open source memory compiler. So Now, in terms of the software kind of maintainability, so we do provide a really detailed regression suite. It uses the Python unit test framework and coverage metrics. We get about 80% code coverage. And I said it's 60 minutes here. Actually, switching to SICE as my main regression simulator, it goes down to about 15 minutes. So,
Wow.
and I also got a big many core machine, but that's a pretty good result. And so any pull request, I basically run through this flow to make sure it doesn't break other things. And that includes stuff for physical design, timing simulation, functional simulation, multiple technologies, and so on. And that's, I think, one of the main, we started OpenRAM by making the tests first, really, as we made OpenRAM. So I think that's one of the unique features.
Well, that's good software development practice, really.
Yeah, and I'm still learning about basically release schedules. I think that's one of the things I need to work on a little bit with OpenRAM. I have a stable branch and a development branch, and I kind of just push frequently to the development branch, and then every quarter or so, I copy it over to the stable branch. I need to start doing some more strict kind of versioning of, minor API changes versus minor revisions and so on. So I know if some of the early users are probably frustrated with some API changes, but we're settling on some more stability now. So in terms of usage, so as I mentioned, it's kind of a wrapper around a lot of the simulator and verification tools. We basically take GDS and SPICE directly, and we have a GDS representation inside of OpenRAM. We take a subset of design rules in a Python file, and these are kind of a conservative subset just to generate the control logic for the most part. And then we take a configuration script, and we also allow users to basically override any module. And this is one of the other challenges with OpenRAM is we've made it in a way that you can have dynamic importing of things so that, let's say you want to make your own customized decoder that does something special. Like someone's asked me for like a series or a sequential address decoder. So it just goes cycles through memory addresses. You can easily implement that by overriding the decoder and making your own. And so we offer that option for anything from the cell primitives, so the actual bit cells, up through the high-level architectural components of OpenRAM. And then the output views are basically the standard output views that you would use in any tool. Left files for place and route, and a data sheet in HTML, and so on. Now, there's two modes for OpenRAM. There's a front-end mode and a back-end mode. The front-end mode is basically intended for users that are system designers, architects. So this is where you want to basically generate memories that you can kind of get an idea about what the size and performance are, but they may not be complete in terms of verification. So there isn't final DRC LVS, and the power is estimated analytically. We're actually adding another way. Right now, we basically have kind of a simple, it's a cacti-like model for power and delay estimation, where it uses mostly Elmore delay type models. We're actually adding a kind of machine learning regression model where we basically use a bunch of memories to predict what options will result in what power and performance. And that should be released. It's in there now, but it's not turned on by default. And so we're doing that as well. And then the more data you have about a technology, the more accurate you can get. In the backend mode, this is where it can basically do full LVS and DRC, and then it can actually do simulated power and delay, and it can be back annotated simulation or not. And the reason I don't turn this on by default is it's really slow. Obviously, simulation of a memory structure is going to have a lot of devices. It's much faster in SICE. We're actually finding orders of magnitude faster than ngSpice, the other open source simulator. And so we can probably think about doing a little bit more of this. We also do some smart things, like we trim out kind of unused portions of the circuit so you don't have to simulate the full thing.
I was going to ask that. Yep.
Yeah, we do kind of a donut model where you just have kind of the edge stuff of the memory array to kind of reduce the computation. But we don't do that in the back annotated model yet. So that's actually a challenge. how to extract that out.
Right, right.
And bit cells, we support anything. We support any number of bit cells in our schematic model, but we only support up to 2-port in physical design right now. That's just for ease of placement of decoders and read circuitry. But there's nothing that wouldn't support more ports for that. And we do standard 6T cells, but it doesn't rely on it being a 6T cell. You could add in an 8T or something like this. It's really kind of agnostic what's inside the cell. And as I mentioned, we do accommodate foundry bit cells. So you can have kind of a black box view as well. Here's an example of kind of the Skywater technology. On the left, I have basically the actual bit cells from that technology. On the right is a DFF from the Oklahoma State library for Skywater. So that's I forget how many track tall, and we see roughly a 5 to 6x smaller SRAM bit cell compared to a DFF. One of the challenges we found with Skywater is that I mentioned it does have the lithography correction, the OPC in there. And it also has kind of the strap cells and these things that basically tie together word lines and tap the end well and so on. And the OPC is actually made with certain restrictions on the placement of the tap cells. So basically what you end up having to do is use kind of these cells with the taps in most of the cases. So you don't end up with kind of this minimal single port bit cell. It's a little bit bigger with the overhead of these other parts, but it's still much, much smaller than a DFF. You still get 5x reduction in area for the array. And you can see here the OPC that comes with it. They basically do for the single port bit cell. This is the dual port bit cell. No, this is the single port bit cell. They do OPC on the poly, Li, and the diffusion layer. And it's a simple rule-based OPC where they just basically do some expansion of edges. And I actually have those rules that they've publicly given me, so we could do some things with those with new designs. And that's something that's pretty unique in terms of a publicly available memory compiler. But this also restricts what we can do. Unless we can redo the OPC, it's harder to make a lot of changes to this design. Now, in terms of the architecture, so I mentioned I'm focusing on kind of what I call a kind of single bank design, but we do have infrastructure to do up to 4 banks at a time, but we've kind of not been maintaining that and just focusing on a single bank as shown here. And the idea of a single bank is you have an array. That array can actually be hierarchical, where you can have basically local arrays or sub banks driven by local word line drivers. So that lets you expand to a fairly wide memory array. Then we have an address port with a hierarchical decoder and the word line driver. We also have a data port, which includes the column mux, sense amp, and precharge and write driver stuff. And then we also have the control logic with timing circuitry. Now, the control logic with timing circuitry right now, we basically do a replica-based timing where it actually uses a column in the bit cell array that drives a 0 on the bit line. So that's kind of a self-timing approach. That's had challenges integrating with certain technologies because you do need a slightly modified bit cell to do that. And so this summer, we're working on making not only a regular kind of delay line based timing, but we're also going to be integrating that asynchronous interface from Yale. So you'll have basically 3 different control logic options in OpenRAM. And I think that's going to be an exciting addition to the project. Configuration files, we just use Python for the designers to tell us, what kind of options you want for the memory and also what corners and kind of scenarios to characterize. You can do the number of things like, number of words, size of the word, the local subbank size or subarray size, the process corner, and the loads and slews to characterize for kind of the stuff that goes into the lib file. And then you can also override the custom modules in here. And I should mention that you can override modules either at the user level, so kind of per design, or you can do it per technology, like the bit cell. Like if you want to have a customized bit cell for a particular technology, that can be part of every memory as well. And so we allow both of those options. And we provide a number of examples with the design, including a number of memories that are common for RISC-V. Typical configurations used in most of those processors.
Is most of I'm just going to ask: is OpenRAM written in Python itself, or what language?
Yeah, it's all Python.
Okay.
Yep, everything is in Python. It has the GDS stuff is actually a Python library that was originally from some people I know at Michigan. It's called GDS Mill. They don't really maintain it anymore, and so we kind of maintain it inside of OpenRAM.
Okay.
But everything else is just Python and OpenRAM.
Okay.
Yep. If I went back, I would probably think about using some of these open databases now, but those were not available. Like not OpenDB, I think, for example, is part of the DARPA project through San Diego.
Right.
But
Right.
those were not available at the time. So,
Martin, did you have a question?
Yeah. Interesting. I mean, so if you're saying in lieu of something instead of GDS2, how would that work then for integrating with other GDS designs? I mean, are there translations?
So we actually do read in and write out GDS directly.
Okay.
Yeah, and then internally, we basically have a data structure that holds the netlist information and the layout information.
Oh, I see. Okay.
Yeah. Yeah, and it's not super full featured, but it does basically what we need to do. And you can do things like some simple primitives like with wires and so on. And I even have actually for power routing, I actually have a very primitive router. It's by no means good, but it basically gets the thing design done. And one of the challenges obviously is on and off grid pins. And basically that's something we need to kind of address in the moving forward is I address off grid pins by just making the grid size of the router bigger. And so then you get rid of the problem of off grid pins, which may not be the best solution, but it's what we're doing right now.
Hey, Matt, this is Warren Nikolic from Berkeley. A quick question. When looking at Sky 130 produced layouts, we see perhaps a bit more of a use of a router than we would expect in a finished memory array. Usually, you expect memory arrays to be abutted. That there is almost no router used between the decoders.
So the only thing we route is the supply voltage.
Mm-hmm.
Like we route the supply voltage, and actually there's also an escape router because in the open lane, open road flow, you need pins on the outside on the perimeter. And so the escape router will actually route pins that are otherwise internal to the edge of the memory. And so those are pretty much direct routes because there's not really any blockage. But yeah, the supply routing there's a number of options for the supply routing. You can either do and this is another thing that was challenging with the open lane, open road flow is their power supply router in that tool is very limited. Basically, you have to have power stripes to connect to their power routing. And so we actually have added, we used to have a gridded power router where we would just put a grid over it and connect everything to the grid. And a lot of the commercial tools would hook up to that fine. But then in the open lane, open road flow, we basically had to add a power ring around it, and it can only connect to the power ring. So they actually, in the first tape out, they did kind of a hack where they took OpenRAM and they basically added stripes on the side and connected the power to the stripes on the side by hand, because they didn't tell me that it wasn't working with the tools nicely. And so I didn't know I had to patch it. But does that answer your question?
Yeah, it does. But also, I'm also not sure why you're using power, routing. Why not just stitch everything together with the power as well?
Well, because this has to be portable to many technologies, and so it's a lot of the things are connected by just stitch being placement. For example, the array is connected, the decoder is connected. Each of the address, the address part, the data part, and the array and the control logic are all connected kind of on their own. But then at the chip level, we need to connect the power, or the memory level, I guess.
Okay, I mean, I probably have some examples, and we can take a look at those to try to understand the intent there. Yeah, go ahead.
Okay. Yeah, and so I mentioned the replica bitline timing approach. This is basically what we do, where we have a column with special replica cells, and then an extra row with dummy cells that kind of don't affect the bit lines in the blue. And then we turn on the replica row to start sensing from the red column, as well as the word line we're actually accessing. And then this gets sensed. This goes through basically also a small delay line to account for the address decode, and determines when to turn on the sense amplifiers. So this isn't a new thing, but this is kind of the Horowitz approach, and it is what we've been using so far. And as I mentioned, we're going to be replacing this with a non-replica approach and also an asynchronous approach moving forward. Hopefully by the end of the summer for the next Skywater tape out. Yes.
I think Sky 130 uses a little different trigger. I think it's a falling edge, right? Or
I don't know what you mean by Sky 130. The memories?
So yeah, the design, I think OpenRAM generated, and somebody should correct me who played with that if I'm not correct. I think it starts decode on the rising edge and fires the sense amp on the falling edge. So
no, yeah, so you're actually kind of correct. It does the pre-charge during the high phase of the clock, and then it does the access in the negative edge. Yeah. So this all happens on the negative edge.
Okay, and all right, thanks.
And we just did that for simplicity in the first iteration, and that's why replacing it with a delay line pulse-based approach would remove that need. But it does put a lot of the delay in the second half of the clock cycle, but it's it works, and it was straightforward to do. And if you have fixes, it's open source. We will take suggestions. So that is that's why we're here. We want to improve collaboration with people. Yeah, so we've also added hierarchical word line stuff with the local arrays. It's actually interesting where we do arrays in a way where we can you can kind of configure how big you want the local arrays to be. And so we've had this working for a while, and this isn't working in Sky 130 yet, but it's working in the other technologies, and it just has to be debugged in Sky 130. We also added write masking, configurable write masking, specifically for RISC-V. You can actually configure it anywhere from a bit write select all the way up to full word write select. And so obviously RISC-V likes to use byte write masking. And so we have done a lot with that. And you can see the implementation here. And then in terms of designs, so we've done a few different versions. This was the version we taped out last year. This was a early prototype with just not a lot of time to get it done. And so we put a RISC-V on 2 chips. One is with a RISC-V core. This was just a 1K memory dual port, and that was taped out. This chip actually, there's a power supply routing issue, so I think they were not able to get it up and running. That's outside of the memory. But then we actually had a separate memory chip as well. And you can see here why we have the power routing, because basically when we pack together the memory, the control logic is in the lower left here. You can see there's a little bit of unused space where we do want to improve and do some kind of better floor planning, but it's made to work with a large number of configurations. And I think that's the thing you're going to find with a lot of memory compilers is they'll only support like 8 configurations because they pack them in such restricted ways that they can't offer other options. And we basically do a lot of relative placement at this level, which lets you make a lot more different options. And so that's why we kind of do basically power routing to connect together these different supplies. You can see a little blank space in here in the bottom that was an unoptimized channel route. The metal is turned off here because we also had the power grid over this, so you couldn't see anything with metal 3 and 4 on. And so that's turned off in this view. And so this was the initial thing just for prototyping. The goal was functionality, and it works. We were doing some additional testing on it just to get some kind of voltage and different corner analysis and stuff, and that's ongoing. The newer memories, so here's some newer ones that we've done. We've done a power ring in this. We also didn't do the proper deep end-well isolation in that last one, so we do that in this one. There's an optimized channel route here. You can see the escape routing of pins to the perimeter so that it works with the open lane flow and the open road flow. Otherwise, everything about this is a little similar to the previous one. So this is a dual port as well. Not much else. We're taping out a number of memories with this now. So this was our, we're doing a tape out. It kind of closed last Friday, but we're doing updates to it still with eFabless and on the open lane flow. And you can see here, this is the Caravelle multi-project wafer chip on the left. And that has a RISC-V processor. And if you look at the host storage, that's actually OpenRAM in the bottom left here. But in the user space, we're actually putting in, I think we actually have about 8 memories now of different sizes. On the right here, it just shows 6 memories of the same configuration because we were just testing the infrastructure at the time. And so we packed in a number of memories that we're going to then single port and dual port with a variety of configurations for testing moving forward. And then we'll have some silicon proven designs. And we've also done work with commercial tools. Here you can see some of the earlier work that one of my master students did with, again, a Pico RV32 and a 45 nanometer process in Design Compiler and Cadence Innovis. You can see left was the flip-flop implementation of the Pico RV32, and on the right, we replaced both the data memory and the register file with OpenRAM memories and got considerable savings. And here's the key. There were some optimizations as well since then. So you can see some wasted space in the memories, but you can see that, even though the memory array is not the most efficient, its improvement over flip-flop based is still huge. And I think that's the kind of the thing to look at now is technology portability versus if you want the most optimal area, you should custom design your memory by hand. If you want a technology portable solution that's easily usable, you can do something with OpenRAM and that'll give you a pretty good solution, but not the best solution. And so in general, we basically got this flow up and working. We generate layout functional models in the circuit. It's open source. You can download it now. We're actively porting it to different technologies, including probably a 90 nanometer in the fall. And we're continually adding new features. That's one of the things with OpenRAM is we offer a lot of flexibility that other compilers don't. Other compilers will generally only allow a limited set of configurations, where we allow a very large number of configurations. And along with that comes a little bit more responsibility of designers, that they have to do verification to make sure it works. But it's kind of a trade-off. And we are also basically offering a library of IP for people that don't want to run OpenRAM. So you can just kind of go and download the memory you want in kind of an existing model. And so we're seeking feedback and also collaborations. And here's the link on GitHub and my email if people want to ask other questions.
Thank you, Matt. Are there any questions from the audience? Further questions?
Hey, I joined really late. I'm sorry about that. I'm just wondering if the presentation is going to be published as well. And can we have access to the slides?
Yeah, I can share the slides. That's not a problem.
Thanks, Matt.
Yeah, and the presentation is being recorded as well.
Great.
I just have
Matt?
one fact. Oh,
Go ahead, Martin. Sorry.
I just have one practical question about using OpenRAM. You know, you mentioned you're providing lots of libraries, which you've already validated. In terms of time investment, how long does it take to use OpenRAM in terms of manpower and the validation? How heavy is that compared to using a commercial tool?
So you mean making a memory in a new technology, or?
Yeah, making a new memory, a new technology, making a new geometry.
So I can't really answer that, since I have not used any of the commercial memory design tools.
Okay.
I'm actually intentionally not doing that. So
to avoid trouble. Okay.
yeah,
That makes sense.
now I can comment on porting OpenRAM to new technologies. So we've done basically 4 technologies now, the 3 I mentioned, and also another proprietary technology. It's getting easier. As I mentioned, every technology has a new kind of hiccup. I think Skywater had a lot of unique features. Actually, one unique feature, for example, in Skywater was I've never seen anyone actually use Cadence and GDS has like the layer purpose pair. The purpose actually distinguishes different layers, not different usages in Skywater, but different layers. And so we kind of had to redo some things like that. And so, yeah, it's getting better, is how I'll phrase it. I think if you have someone that's familiar with OpenRAM and a working PDK, it could be on the order of a couple months for like a designer, a good designer.
Okay. All
So
right.
I think on that note, ready for the next question. There were a couple of things probably in that surprise camp, kind of pending for the ongoing Skywater tape out. Do you mind a note or two on kind of what those are and how the outlook's looking there?
Wait, what do you mean? Can you repeat that?
I think at least as far as the pre-published stuff that you guys were still working on a few tweaks to enable the ongoing Skywater tape out.
Mm-hmm.
How's that stuff going? And
pretty good. Yeah, we released a number of the dual port memories. I think a 1K and a 2K, which are pretty good. We also released a 4K and an 8K, which I think needs some more functional verification, especially the 8K. I think I have to go to a sub array to get it to actually work. We also have single port memories that are a bit different in the way we design them. The way we did the dual port to get it done quick was we took the Skywater cell and the kind of strap cell and made kind of a custom bit cell that we used. Whereas in the single port, we actually decided to write custom modules for the array generation in Skywater. And so we kind of went through that infrastructure to show that you can have just custom code per process to make a different array layout, as an example. And so we have that working with single port as well, which because we were testing that, it took a little longer than we had expected. But so we have a number of single port memories on there as well. ranging from, I think, 1K to 4K and up to like a 64-bit data word. So
Hey, Matt, would you be able to describe the software architecture a little bit of OpenRAM? I'm just kind of curious as to what the main pieces are of it, and also then just to get a sense of how easy or hard it would be for the community to add different things to it.
yeah, so we basically we have a class that is a module, and that module has a layout view. It's derived from a layout view and a what we call a spice view or a schematic view.
Right.
And so we basically have representations of, devices and ports in the spice view, and then we have equivalent views in the layout. And so you can kind of go through and basically add instances of things and route things together. So we have auxiliary functions to basically add wires, add ports, add pins. And so there's a lot of kind of helper functions to basically do a lot of that stuff.
Okay.
And the same class is used to implement everything from the bit cell up through the memory, where it's a module with ports and so on. And so it's a full hierarchical database view.
Okay.
And and it's basically the responsibility of every module to define, what is its interface, what is its boundary, and that lets other things put it together, compose larger blocks out of it.
So I'm just curious for the timing models, do you actually do like cross sections of it and then put that into Spice, or what exactly do you do?
So what we do is we dump out the entire thing and basically don't dump out certain cells. So we can flag cells as kind of trimmable cells.
Okay.
And it's up to each module to decide what it can trim or not.
Okay.
Like I mentioned, the array, we typically keep the left, right column and top and bottom row of an array.
Yeah.
So that lets you kind of do the extreme corners of the array.
Okay.
And then, and I should mention, in terms of the timing model, a module also has a timing and power associated with it. So that module determines how it wants to model its power and timing. And so most of them default to kind of a simple Elmore model. I think for the leaf cells, like the bit cells, you could actually just say its leakage is this, and it'll kind of scale up. So yeah, that's something that I think we're working on, that, I mentioned it's kind of an Elmore type model, which is, I think, a little more accurate than something like Cacti, but you need to give it the right coefficients, resistance, capacitance of wires and devices to kind of calibrate the model.
Right.
And so we haven't done a lot of that in Skywater yet. We're focusing on, I think the regression model actually just has a better, is more useful, I think, where you just give it a bunch of memories and have it fit a model statistically and say, this is what we think the power and delay will be, at least from a high level user.
What's the most advanced technology node that OpenRAM has been tried for? Do you have a sense of that?
28 nanometer.
28. Okay.
Yeah. We haven't released that. The Yale people also that we're working with also did 65 nanometer. And actually the 28 nanometer was early on in OpenRAM. So I have not maintained that actually. And we actually looked at doing free PDK 15, but from looking at that, the design rules and stuff are actually kind of limited. It's not a really good representation of a 15 nanometer process.
I see. Okay.
And then I was talking with, what's his name, Clark, about ASAP 7, which is another predictive model. But they actually had some issues with the licensing where you couldn't redistribute anything. But I think that since then they've come out with some memory models, some memories of their own, actually. And they might have redone their license. So that's probably worth revisiting.
They did recently change their license significantly, I don't know, maybe 2 or 3 months ago, I forget.
Okay. Yeah, I haven't looked at that since, because I was trying to get him to, license it differently, but they weren't having it.
Yeah.
So
it was also strictly non-commercial before that, which sort of set us off, but.
Yeah, exactly. And yeah. But those design rules in that kit looks fairly good. And so that's why I think, if we can get it working with something in that technology, that would be a huge move forward, I think.
Oh, that makes sense.
Hey, Matt, Bona speaking again. First, I want to thank you for doing this thankless work. I mean, it is really important to have a memory compiler. We do have quite, as Dan inferred, we are seeing quite a few challenges in trying to use it in Sky 130 and Sky 130 and later Sky 90 will be our priorities to have a good quality output in these technologies. So the question is here, how can we help get this memory compiler produced things that is comparable to what you would see in the commercial world?
Yeah, I mean, you said that you've been,
the most,
that's a good question. You said you've been using it and having challenges. What are those challenges? I haven't heard about them. So I guess sharing and filing issues and kind of following up with things, that would be useful.
Yeah. Dan, do you have a quick list, or should we set up? It's 9. Should we set up a separate call?
What do you mean a quick list?
I'm asking Dan Fritchman, who is on the call, who has been trying to get this shipped through.
Yeah, why don't we follow up?
Okay, yeah.
I think that would be great. So we are almost out of time. Are there any closing question or comments? Well, Matt, I want to thank you for an excellent presentation today. I thought it was very informative, and it is an important area of work. I know from my own experience that many companies do, in fact, roll their own. So hopefully this will provide a foundation that the industry can build off of, and also provide additional research and help for the community that you are building.